going to talk about design lessons from nature and what I call biological inspiration. And I will define that. Just to tell you, I founded a center called CiBER at Berkeley, the Center for Interdisciplinary Biological Inspiration in Education and Research. And we actually run a course that's going to hopefully occur in the spring for architects and designers and business people on bio-inspired design. If you're interested, come and talk to me. I think we are truly in the technological age of biology, where many what I call bio-mutualisms are being formed. That is, associations between biology and other disciplines, where each discipline reciprocally can advance the other, and the collective discoveries that emerge are beyond any single field that you see. Now, why is this? Well, it might be perhaps what Da Vinci says, and that is, human ingenuity may make various inventions, but it will never devise any inventions more beautiful, nor more simple, or more to the purpose than nature does. Because in her inventions, nothing is wanting, and nothing is superfluous. Or more contemporary claims, like, there's nothing to invent that is not already present in nature. Or in a review of a book called Biomimicry, the utter technological superiority of would-be lower life forms. What we should do is biomimicry. We should copy or imitate nature closely. Well, let's look at it more critically. How much has nature inspired so far? If we look at the greatest engineering achievements of the 20th century, very few of the breakthroughs have been inspired by biology. Why might that be? Well, until at least recently, human technologies differ greatly from natural technologies. Human technologies tend to be large and flat with right angles, stiff things with lots of rolling devices, axles, very few actuators or motors and sensors that mostly do one thing. Whereas natural technologies are small and curved, they bend and twist, they have lots of appendages and many actuators or muscles, huge numbers of sensors, and they do a lot of things. Pretty different technologies. So really, being an evolutionary biologist, as well as interested in biomechanics and physiology, we absolutely don't recommend copying nature. Natural selection is not engineering, and evolution actually works on the just good enough principle. Not perfection by any means, not optimal. There's a difference between evolution and engineering that's important. Engineers often have final goals where biological evolution doesn't. Organisms often have to do a whole bunch of things, whereas in engineering you want to execute a few tasks. Trade-offs in biology are the rule, so severe constraints are pervasive, and global optimality, you almost can't find it. Biological evolution really, you should think about it this way, works more as a tinkerer than an engineer, and tinkerers never really know what they'll produce and use everything at their disposal to make something workable. That's really what you see in organisms. They have severe constraints, if you think about it, with respect to design. They have to grow. If I told you you had to make an automobile this big and then full size, and they had to work all the way along and not be eaten, this would be pretty tough design constraint. They also have functional constraints. The part that you care about, that you want to do something wonderful, also does a bunch of other things. So it's compromised in design. That's called a functional constraint. And the worst one, of course, is that you can't throw away your history. Right? You have legacy code there and genes, and you have to modify them a little bit. This is a historical constraint, evolution. And the worst one is the part you may be looking at, maybe an adaptive solution to another problem. And it could be non-optimal. Like the birds of paradise have beautiful tails, and you might think that's wonderful for flying and pitch control, or it just makes the bird fly badly. But it's very attractive to females. And so therefore persists and develops, you know about peacock feathers and antlers and these strange things. It's called sexual selection. Right? Now those are obvious ones. What about all the less obvious ones? Do you really want to copy that part? This is what Darwin said about this. He said, "What a book a devil's chaplain might write on the clumsy, wasteful, blundering, low, and horribly cruel works of nature, upon very careful observation." But nature's technology really represents our only known alternative at the moment until we meet people from outer space. And so really looking at nature designs, in a sense, liberates us from the constraints of our own habits and history and outlook. What should we do instead? We think you should be biologically inspired with respect to design. And by that we mean something very particular, and that is using the principles and analogies from biology when they're advantageous and integrating them with the best human engineering to design potentially something better than nature. For example, this is an extraordinary bird, one of the largest birds ever evolved. But you didn't fly here on a bird. Planes are pretty good. They can take hundreds of people around the world, and there's no bird that can do that. Engineers have made incredible advancements, and that's not from nature. But what's wonderful at this time is that as the human technologies take on more of the characteristics of nature, nature does become a much more useful teacher. And that's what we're seeing. So yes, there has been inspiration. It's true that the plant sticking on someone's pants helped to inspire Velcro, and that you can look at boxfish and their low drag to build new kind of cars. Or you can use the wonderful capability of the lotus leaf in self-cleaning to put together some interesting new paints. And you can look at the reducing of friction of the scales in shark skin to build faster swimsuits. You can look at flies who are pretty amazing to make microflyers. And as I'll show you, you can look at geckos to produce a new kind of adhesive. So it's happening. And so what I want to do tonight is just to go through a few design lessons from nature with you, with examples from the kinds of work we do. The first, I've already told you, which is evolution is not human engineering, and we strongly advise to not blindly copy. All right, what have we learned from nature that's extraordinary? Let me talk about the first one, which is that we see from nature that, in general, you need to work with the natural dynamics of the system. By that we mean managing the flow of energy. Now you might think for motion, which is what I study, that, well, this is a solved problem. The best way to manage energy is to make a wheel. So if you have to have legs, then you would do this kind of thing. Well, it's kind of hard to make a wheel with appendages, but Escher in '51 drew a creature he thought was novel that rolled. The problem was, several million years before that, nature had already evolved this. It's called the stomatopod. And here it is. It's a shrimp-like animal that actually rolls on the beaches of Panama. It does backward somersaults, and for half its cycle, it's actually like a wheel. And the other half, it's like a leg. So that's about as close as we can get. There are things, of course, that fold up in balls and roll downhill. But I can do that. So it's not, this can actually roll uphill. So very impressive mode of locomotion. But one of the most beautiful energy management systems that we have is seen in walking. In simple walking, you actually work like a pendulum, exchanging energy back and forth, except the pendulum's inverted. So as you swing up, you have all your potential energy, and that goes into kinetic energy as you fall forward. You swing up in potential energy, and you can exchange the energy beautifully, just like a pendulum. It's extraordinary. How extraordinary is it when you work with the natural dynamics? It's this extraordinary. So years ago, people were able to take this robot and put it on a slight incline and have it walk. Why is it extraordinary? It has no motors and has no sensors. Right? So it has perfect natural dynamics to produce the walking gait. This is really extraordinary. Now we don't look at humans, but we look at these animals. If you could turn the spotlight down, it would help a little bit maybe on the video. This is actually a cockroach running on a treadmill. Can we turn that down a little bit, or is it possible? There goes a scorpion, an ant. There's a centipede on a treadmill. And this is a ghost crab. It can run up to 4 meters per second on the beaches of North Carolina, sideways. Pretty extraordinary. Now you say, those are just strange. But they show energy management too. Not like a pendulum, but they store and return energy because they work like a pogo stick. When they're running, they all produce the same ground reaction pattern. That is 2, 4, 6, and 8-legged animals. And they all bounce along like this kangaroo. Because your one leg works like 2 legs of a trotting dog, or 3 legs of an insect working as 1, 3, 3, 3, or 4 legs of a crab working as 1. All bouncing along on this spring and producing this force pattern. In fact, it's so extraordinary that if you were to look at the stiffness of the springs of all those and correct it for size, what you'd see if you plotted the smallest animals to the largest animals is that they all have the same relative stiffness of their spring. So the relative stiffness of your leg spring is the same as a cockroach. Now, this is a general principle that we discovered then about locomotion. And you can imagine we wanted to see how general it was, and this could then provide inspiration for new robots. So in the final design of a robot that we produced, we looked at its relative leg stiffness when it was most effective, and it follows this general principle. This is the robot Rex for robot hexapod that can run up to 3 meters a second and is bouncing along and producing the same forces on the ground that you do when you run. It just does it with 3 legs at a time. But it's very springy. This is the commercial version from Boston Dynamics, going through incredibly difficult terrain. So you can see it going through rocks. And look at this surface. Pretty challenging for a tractor or wheeled vehicle. But for legs, it can do it just fine. So you can not only do this with that size scale, but you can scale it up. So here's the first effort from actually a show of individuals who only worked on this for 2 weeks and produced a potential vehicle that you could sit in to bounce along like the robot. Yeah. It didn't quite work. It actually had some motor problems, but it's not impossible. It's not impossible to scale it up to get it to work. All right, and you can also do this with 4 legs. So here's a big dog from Boston Dynamics, the same company that makes the Rex that we worked on. This is 4-legged version, carrying heavy loads. Perturbations with a very simple control algorithm to stabilize itself. Here it is slipping on ice. We can all relate to this. The galloping version. That's it. Here's their latest creation called Petman, which is the sort of bipedal version of the big dog. And it also has the same stability. This has a lot of interesting features, one of which that we show here is that they have reasonably natural contact during walking with the heel and the toe, if you look at it. It's very interesting to explore human gait. All right, well, you can use these same general principles to set the relative stiffness of prosthetic devices for individuals who are disabled, to restore their function again, right? Same principle works. In fact, this led to a controversy. Oscar Pistorius was initially banned from using these spring-like legs from the Beijing Olympics, although through tests from some of my colleagues, they showed he really didn't have an advantage, and they ruled he was eligible, but he missed qualifying by 0.7 seconds. But stay tuned, he wants to race in the London Olympics with this relatively simple leg. But it relates to a larger question, is as we replace more of our parts, and our parts can get better and better, maybe disabled individuals could choose to be superhuman. Or at some point, will we choose to be superhuman by removing the parts that we already have? I think these are really interesting questions that we'll face. But probably we'll just enhance natural performance first. So here are the same sort of spring mass bouncing capabilities in this ad from Power Risers of individuals moving around. I'm not sure we're quite going to be all wearing these, but it's interesting possibility for enhanced performance. Although this looks really fun. If you look at this, that looks really fun. Watch this one. Pretty incredible. So, you can see working with natural dynamics is important, is managing energy flow. And whatever you think about when you interact with an organism or a human is critical to think of. The dynamics are important. All right, the next lesson I'll talk about is an effective interaction with the environment, where really the organism and the environment can't be considered separately. And that's because when we look at movement, the surface has holes in it, it slips, you have different types of footholds. That interface is critical. Our favorite animal for studying this is the gecko. And we want to know why it can do this. So this was from a television show. It was climbing up the plexiglass, slipped, grabbed on by one toe, and just didn't care. Just put it back up. It's amazing. And this is the reason why it's incredible. These are the feet of geckos. I know you might think these are like alien drawings or something, but these are the real feet. Why do they look like this? I still don't know. If you want to come in or send your kids to figure this out, it's a great question. We don't know the answer to this yet, but we know it has something to do with sticking onto things. Because we can study it on this treadmill. It's a gecko mill. This is a see-through treadmill that you can actually see the toes do stuff. So we can see how they use it when they're actually locomoting. And the thing we discovered, pick a toe and watch it. And see if you see what it does. It uncurls, it peels. Kind of like a party favor that you blow out. And it uncurls, goes back. They do that with their toes. And they do it in tens of milliseconds. All right? You watch it, you can watch it peel back that way, there. Isn't that weird? So they can do this. Now, how do they stick onto stuff? Well, they have these leaf-like structures, and on these leaf-like structures, if you blow them up, they have millions of hairs. And the secret is that each hair has the worst case of split ends possible. There's like 100 to 1,000 split ends, but they're nano-sized. And so an animal has 2 billion nano-sized split ends. They don't stick by glue or by suction or by Velcro interlocking. They actually stick by intermolecular forces. By van der Waals forces, they just get very close to something. And there's a lot of them. A lot of weak forces add up to be pretty big. And so what's exciting is that you can take now the simplest real versions, and my colleague Ron Fearing at Berkeley is making the first self-cleaning dry adhesive that's synthetic, which is really exciting. We continue to work on this. We're pleased to report that there are a huge number of applications possible, and so many different groups that are interested. Not only adhesives, but also in sports, biomedical applications, technology, robotics, automobile. Here's one for tires. And there's both sort of easy release adhesives that will be more near-term development, and we think longer-term controllable adhesives will come to be pretty extraordinary as well. So stay tuned for the Gecko product line as soon as the manufacturing gets cheap enough, which is a challenge. But the interesting thing about it is you could potentially use larger hairs than the gecko does if you understand the other general principles of how it can stick. My colleague at Stanford, Mark Krakowski, did this and built some of these hairs, a directional adhesive. And he was able to do this. This is my former graduate student, professor at Lewis and Clark Colorado. This is Songbei Kim, now a professor at MIT. This is my student's firstborn child. And so he is now hanging her from the adhesive. For the first time, a human was hung from the adhesive, and it works pretty well. At some point, maybe this can happen.
Lynn Verinsky, a professional climber who appeared to be brimming with confidence.
Honestly, it's going to be perfectly safe. It'll be perfectly safe.
How do you know?
Because of liability insurance.
With a mattress below and attached to a safety rope, Lynn began her 60-foot ascent. Lynn made it to the top in a perfect pairing of Hollywood and science. So you're the first human being to officially emulate a gecko.
Wow, and what a privilege that has been.
So she actually had trouble with just the hair, so there's claws on that one, mostly grabbing on. But you know, geckos use all the stuff, not just the hair. So, but stay tuned. People are working on a suit and gloves to do this, so it'll be very interesting. Now, to put it on a robot, well, the problem is actually unsticking. It's not so easy. But remember what the geckos do. They peel their toes away like that, right? So my colleague Mark Krakowski at Stanford and student Songbei Kim produced StickyBot. And so take a look at, StickyBot has the big hairs on it. Take a look at StickyBot's toes as it climbs up the wall. It's doing the gecko peeling for release, which is actually a pretty good strategy. You can imagine it climbing up your cupboard. See it? And I want to show you now an example with this system of a bio-mutualism that occurred. The engineers said, you know, we made this robot, this one's called Rise, climb up the wall, but you know, it needed a tail. Because we didn't put a tail, it kept falling backwards. And they asked us, well, do the animals use their tails during climbing and maneuvering? That's a well-known fact that they didn't, right? And we actually measured it ourselves. But they gave us this wonderful question that produced a new hypothesis in biology. And so we went and tested it. And we made a new discovery. Well, if you make the track that the animal runs up easy to grip, it doesn't use its tail, which is what people discovered before. But if you put a slippery patch there, it turns out that they use their tail as a sort of an emergency fifth leg for stability. Here you can see it. Here's the slippery patch. This is slowed down 10 times, because you can't see it at regular speed. The animal will slip, and it's going to fall back, and watch its tail. Oh, and it pushes it back. This is a reflex, and it's really fast. It's in the millisecond range. Well, then we told them, well, you should design active tails, right? Not just little bars that you stick on the end. So this is happening. This is the earlier version of it. In fact, this is sped up 5 times, so that robot's actually quite slow. But you can see the kinds of things that an active tail could do. Stay tuned. We think most robots will have active tails. And you'll see why more. So that was interesting. You can see the nice mutualism there. Oh, then we wondered, why do these geckos have such active tails? What else could they do? And so we thought about, well, if they're climbing up the wall or a tree, and then they climbed up on the underside of a leaf, what happens if we shook that? So that's what we did. So here's the equivalent of a leaf from the side and the front. Gecko's on it, we shook it, and it falls off, but watch what it does. It's the world's fastest air riding response. So it's kind of like a cat, except it doesn't twist its body. It just swings its tail around. You see that? Just with its active tail. And so we said, well, how hard is that to do? Let's make a robot do it. So there's the robot. No problem in doing it relatively easy. It's just a spring. So then we wondered why they do that. There's no recorded data about them gliding in nature, but we thought we'd test it. So we took a wind tunnel, blew the air up so a vertical wind tunnel as if you were gliding down, and then put a natural landing target there, as if they could glide to a place. And we tried to see what they did. And here's what they did. They can actually do equilibrium glides. I don't know if we can turn the lights off the slide a little bit. It might help to see it better. There it is. So pretty extraordinary and beautiful. They can fly too. But the neat thing is they use their active tail. So we found that they can swing their tail in one direction, turn left, swing their tail in the other direction, yaw right, and so they can actually steer while they're gliding. Then they do this, which I don't even understand. If you can tell me what this is. They can oscillate their tail up and down like they're swimming in air. And if you watch carefully, their front legs are doing this. You see this? Could that be anything to do with the origin of flight? Like down from trees, you start doing this to control gliding, and then you develop wings. This is ridiculous speculation, but interesting to think about. But incredible movement, right? And we still don't understand. Now, are they really trying to land somewhere? Well, here's the landing target. Let's see. This is from the side. It kind of looks like it's going over there. But if you look down on top, you definitely see that they're trying to go to the landing target. Look at that. Watch it again, how it's trying to land on this tree here. It's outside the wind tunnel. But see how it whipped its tail around to try to go to that landing target? Definitely on purpose. There it goes. Boom. That's incredible. But then we were left with the problem is, well, they can do all these things, but no one's ever showed them to glide. So we thought, we'd better go in nature. And we were concerned, what if they don't glide at all? They can do all these things. But my student went to Southeast Asia, looked at them gliding, and here's the first video of a gliding gecko, this type. There it is. It's at the end of there. It's very hard to see, but you can see it land if you look when it gets in the box. Boom. See it hit right there? And so now we're looking at landing and perching and all those things, and robots to do this too, so stay tuned. But anyway, an effective interaction with the environment is critical, the organism environment one. The last lesson from nature I'll talk about is the use of multifunctional materials that are sort of programmable, integrated, and robust. Organisms do that really well. And I'm going to tell you a story about exoskeletons and a new experiment that we've done. We haven't published yet. You have an endoskeleton. So your skeleton, the bones are on the inside. And most other creatures on Earth have their skeleton on the outside. Right? They have an exoskeleton. So all the arthropods and beetles and all the things that make up the Earth are really this kind of design. Here's one. This is the American cockroach. And the exoskeleton provides support, protection. It's where muscles anchor to. It's for locomotion, sensing, and a whole bunch of other things. If you look at it closely, you can see it's made up of skeletal plates and tubes and compliant membranes between them, giving you an incredibly interesting, robust design. Well, we wanted to look at actually the sensors of the animal. So this was a surprising discovery that I'll show you. But what we want to do is take the animal, run it along a track, and watch it transition and climb up a wall using its antenna. We picked this animal. This is one of the world's fastest animals. It can go at speeds of 1.5 meters per second, which is the equivalent of sort of 200 miles an hour. It's about that big. It's the American cockroach. It's the one you think you don't have in your house. But if you see them, you actually have a lot of them. But they're there. They're everywhere. Now, the thing is that they have long antennae, and if they were just using their antenna, they only have about 10 milliseconds to sense the wall. And so we wanted to push their sensors to their limits to see what went on. So here's what we found. Here's the animal running, here's the wall, and here's what we see in real time. Okay, it looks like it's beautiful. Rapid, smooth, vertical transition up a wall, right? Let's look at it again. There it is. That's what you see. Not much. But then, when we did the experiment, my student says, hey, you have to come here and look at this. I said, why? Well, listen to it. We put a microphone by the wall. What? Now, this is looped, so it's not continuing. But if you slow it down, there's real speed. Now, you slow it down, you see what it does. All right? It crashes into the wall head on to make this vertical transition in only 75 milliseconds. And no matter what we changed, it still does it on purpose. It crashes into the wall head on. It's the fastest way to get to the wall and up the wall. Not to slow down, not to sense things. It's too fast to do it. We change the wall properties, we change the floor properties, we change the lighting, we change the sensors. Full speed into the wall. Now, this is interesting because you can actually calculate how effective it is at absorbing energy, this exoskeleton. And you can compare it to something like a car. And it turns out it's really good. It can absorb 90% energy, where your front bumper is about 91%. That's pretty good at handling that transition. Now, what's the paradigm shift in thinking here? Well, it's that we think of effective performance as free of error, without missteps, and to be very elegant, right? But that's because we're big and we don't have exoskeletons. We need to think about it differently. And so can you put this in a robot? And my colleague, Ron Fearing at Berkeley, has done an incredible job with the students by developing a rapid prototype system for fast designs, where you design it flat like this, you cut it out with a laser cutter, you put a polymer over it so that there are compliant membranes, and heat it up, cut it out, fold it, and you get a robot. And they can actually do this within an hour. This is incredible for us because we can test all kinds of designs on this rapid prototype. You can make a whole bunch of different legs that do different things and see what they do with this kind of exoskeletal design. And they did the same thing that we did in the experiment, crashed the robot in with this energy absorption, and sure enough, it could begin to make a transition. Not quite as good as the cockroach yet, but it's beginning to do it. But the idea now is that the smart technology is built into the body in terms of its robustness. So it's incredibly compliant. And so a strategy then is, instead of careful sensing of exactly where you're going when, that's very challenging when you get small and quick, why not just bump into it like the animals do and just try again? And you lose very short time. It's a very effective strategy. And there they dropped it off an 8-story building. And watch. It can still run away. So other groups, like our collaborators at EPFL in Switzerland, have made a jumping robot. And they had trouble. It always broke. The beautiful Swiss manufacturing would crack when they're... And so what they did is they put an exoskeletal cage around it. It always lands because of a certain shape to jump and take off again. And it's an incredibly effective robot now. You can also do this for flying. So flying through things is pretty challenging. But if it's a problem, if you just crash into it, have the right shape and land so that you can take off again, like the animals do, then it's a strategy, a very effective strategy. You know this experience in your house. You've seen flies do this. They crash into windows all the time. And it's not a problem. They can maneuver this way very effectively. The exoskeleton in these animals isn't dead. In every location, they have massive numbers of sensors. So they're sensing everything. Vibrations, with their feet, and it's incredible how many sensors they have. Very different from what we build in robots now, but that's going to be a possibility. So my colleagues Jarvi and Ron Fearing at Berkeley have developed eSkin that was reported last month. I think they had a paper, which is a pressure-sensitive skin that's made up of nanowires. And here it's sort of sensing this C. So ultimately, we'll be able to put sensing into these compliant exoskeletons, which will significantly increase the capability of what they're able to do. But my most recent favorite example of exoskeletons applies to you, applies to humans, and individuals in particular that are disabled. So a few days ago, my colleague Hami Kazaruni at Berkeley, through Berkeley Bionics, showed the development of the E-legs exoskeleton for paraplegics.
When a person becomes paralyzed, a level of their independence is also robbed from them. and that affects us psychologically and our spirits. There's a part of us that dies. I've been trying to visualize myself a contraption that would enable me to get up and walk. I thought, well, is it going to be an avatar, perhaps a robot? And then I received the phone call to try this new technology, the e-legs. To take my first step in the e-legs was just astounding, because I bent my knee for the first time in 18 years, and I placed my heel on the ground, and then I transferred my weight, and then I took another step and another one, and it was so natural, and that was what really gripped me.
In my field of spinal cord injury, we work with people who typically are paralyzed for the rest of their life. For the first time in history, we can start to think about giving movement back.
They're only going to get better, and there's a good chance that all of us will be using these as we get older to keep our mobility as we have difficulties in aging. So stay tuned. Okay, to conclude, I talked about sort of 4 design lessons from nature. That evolution is not human engineering, so we shouldn't really do strict biomimicry. That working with the natural dynamics and whatever you think about, whether it's sitting in a chair or building a space, that managing the flow of energy is critical in a dynamic sense. That you can't think of individuals or organisms separate from their environment if we want to understand how they work effectively. And that we see organisms use incredible multifunctional materials that you can control and program that are integrated and robust. So what are the actions of the future for what I've talked about? I think there's several that are important in the broad scale. First, I would argue we should demand a deeper understanding of nature. Uninformed copying and manipulation, I think, can be shown to be very ineffective and potentially even dangerous. So that means we all need to support transformative, curiosity-based research. Because I've shown you, you never know which studies will be most translational into something that's important for you or I or other organisms or the environment. And to do this, mutualistic, interdisciplinary collaborations, I would argue, are absolutely required. This is a two-way street is really necessary for rapid progress. When one discipline makes a discovery that elevates another, and that discipline elevates the other, and you do this as a team, and collectively the discoveries are extraordinary. And we need to build on that model. How do we do this? I would argue you have to redesign education for this interdisciplinary approach, not the way we're doing it now. We have to emphasize integration, critical thinking, and innovation. And that's a big job with respect to how schools are at the moment, but important. And of course, finally, conservation and sustainability are essential, because whether you care about search and rescue or restoring function or repair, we must preserve nature's designs. Otherwise, the secrets that I've shown you will be lost forever. Thank you. And come visit our center.